Okay, the second method for determining the enthalpy of a reaction is something known as Hess's Law. And much like with the enthalpies of formation, you're still going to have a reaction that you're trying to find out the heat for, or the enthalpy for. In this case, we have C2H2 plus water plus H2 forming C2H6O. Now, if you're given the delta H's of formation for all of these reactants and the product, you can use that to find the enthalpy of this reaction. But in some instances, you might not have that information. Instead, you might have a series of reactions for which you do know the delta H's for each one of the reactions given. But none of the reactions shown is the reaction that you're interested in. That being said, there are molecules present in the reactions for which delta H's of reaction are given that are either components present as reactants or products of your desired equation. For instance, we have C2H6O as a desired product in our reaction, and it so happens that one of the reactions has C2H6O within it. There's also reactions that have H2 present in them. We have also reactions that have H2O present in them, and we have reactions that have C2H2 present in them. So even though we don't have the specific reaction itself, we do have the major components of the reaction in question present in kind of scramble mode in all of these reactions. So basically what Hess's law is all about is changing the equations here, either reversing them or multiplying them by a balancing coefficient in order to end up with the correct molecules for the desired equation with the correct amount in terms of balancing coefficients. And those changes that get done to their equations also get applied to the delta H value of the equation itself. Now the idea is that we're going to apply changes, and at the end we're going to add up all of the equations together with the premise that the addition will yield the desired equation. Okay, so I'm going to show you how to do that. In this example, we have 4 different equations, and the process is a little bit convoluted, but as I pointed out before, notice that we have C2H6O as a product in the desired equation, and the first equation in the series has C2H6O as a product. And it is the only equation, if you look carefully, that does have C2H6O. So what this tells you is that you actually want to make sure that this equation, which has the molecule that you want in the correct place, namely the product side, with the right amount, you basically want to make sure that you lock this equation in place. You don't change it, you don't do anything to it, because if you do change it, you will change the amount of C2H6O, and by doing that, you'll mess up what you're trying to get at the very end, which is simply 1 mole of C2H6O. So the first equation is locked in place, you can't change it. Alright, now we take a look at C2H2. And C2H2 is present only in the third equation. Right? If you scan carefully, you'll realize that yes, C2H2 is only present in the second equation. Now, C2H2 is on the reactant side, much like in our desired equation, but the difference is that you have 2 equivalents of C2H2. You only want 1. So what that implies is that you're going to have to multiply the entire equation by 1/2 in order to convert the C2H2 into 1 mole. But the application of the multiple, the 1/2 multiple, doesn't just apply to the reactants and products, it applies to delta H as well. So multiplying 2 by 1/2 gets you 1. Multiplying 5 by 1/2 gets you 5/2. Multiplying 4 by 1/2 gets you 2. And multiplying 2 by 1/2 gets you 1 as well. But that 1/2 needs to be applied to negative 1299.5. And when that happens, the value gets reduced to negative 649.8. Alright, so you are in essence trying to come up with the right amounts of reactants and products by changing the equations, but the change needs to be applied just the same to the delta H value. Alright, so since we have now attained the right amount of C2H2 and it's on the correct side, the third equation is also locked in place. So the first equation and the third equation cannot be changed any further. This is as much as you can do with those 2 equations. So we move on to looking at equations 2 and equations 4. Alright, so here we go. Now, looking at the fourth equation, we have a few components here. We have H2 and we have water. Now, what I'm going to do is I'm actually going to switch the equation over, right? So take a look at this. Before we had H2 plus half O2 giving us water with a delta H of negative 285.5. What I'm going to do is I'm going to reverse the equation. So the H2O is now going to be a reactant, the H2 and the O2 will be products. And moreover, take a look at the value right here, negative 285.5. The moment I reverse the equation, this is no longer negative 285.5, it is now positive 285.5. Okay, so multiplying an equation by a constant implies that you have to multiply delta H by a constant. Reversing an equation means that you change the sign of delta H. All right, now you might be asking yourself, why did I reverse the equation in the first place? And one reason is because before we had O2, O2, O2 all on the left side of the equation. And before we also had O2 on the left side of the equation. So the reason I swapped these two was such that we end up with O2 on the right side and O2 on the left side because I need to cancel them out. Notice that in the desired equation, O2 never makes an appearance, so the O2 will have to be cancelled out. All right, I'm going to come back to that in a second. Now, a second thing that's kind of similar involving the second equation in the series is the fact that we have carbon graphite within it. And if you notice in the first equation, which is locked in place, which we cannot change anymore, we have two C graphites. Now the graphites never actually make it into our desired equation, so we need to cancel them out. In order for that to happen, we need to have C graphite on the left side of the equation and on the right side of the equation. So we're going to need to basically reverse this equation. And notice once again, we reverse the equation. This goes from negative 393.5 to positive 393.5. And now, since we have two C graphites on the left side of the first equation, we need to still have two C graphites on the right side of this equation. So that means that we'll multiply everything by 2. And that means that the 393.5 will now increase to twice its value, specifically positive 787.0. Alright, we're getting pretty close to the end. So, since this allows us to cancel out the C graphite completely, that means that the second equation is locked in place. You can't change it anymore. So looking at the last equation, we focus a little bit on a few of the components. First things first. Notice that if you look at the hydrogen, we have 3 hydrogens on the left side. We have 1 hydrogen or 1 dihydrogen on the right side. We only want to end up with 1 on the left side, so that means that we need to multiply this entire fourth equation by 2. Okay, so we multiply the entire thing by 2, meaning that the 285.5 will now be 571. And you apply the coefficients of 2 to all of the reactants and products of that equation. Okay, so what happens now is that the 2 graphites cancel out with the 2 graphites since they're in opposite sides, right? Also, the 2 CO2s cancel out because you have CO2 on the left side, CO2 on the right side. Now, if you look carefully, you have half an oxygen on the left side, and you have 5 halves oxygen on the left side. So 5 halves plus 1 half is the same thing as 6 halves or 3 oxygens. And if you look carefully here, you have 2 plus 1 dioxygen, so they all cancel out. And lastly, you have 3 dihydrogens, 2 dihydrogens, they partially cancel out to give you 1 leftover dihydrogen. You have 2 waters on the left side and 1 water on the right side, so they also partially cancel out to give you 1 water left over. So at the end of the story, you end up with your desired equation because everything else cancels out. And because you now yield the desired equation, you are free to add up all the delta H values that you have changed accordingly to end up with the value of the delta H of reaction. So this is Hess's law, and it's a little bit more convoluted than delta H's of formation because you have to be moving equations around, multiplying by constants, making sure to keep some locked while changing others. So this might take a little bit of practice, but don't be too turned off by them. They're actually kind of neat little ways of finding out delta H's of reaction. Alright, with this, we'll continue on to the next video, which is the enthalpy of reaction. Oh yeah, one more thing I forgot to mention is that because the enthalpy of this reaction is positive, that means that the reactants have lower energy than the products. This delta H value is basically going up in value as a result of the energy being acquired by the reactants, in essence forming the product. Alright, now in the next video we're going to talk about bond enthalpies, and that will basically finish up this particular lecture series.